So the longest chain is 6 carbons, so the parent name is hexane. And that leaves out this thing and this thing. And that is an ethyl. So the ethyl is on what carbon? 4. Ethyl dash. The methyl is on what carbon? 2 dash methyl hexane. All right, so that's the IUPAC name. And that would be the same name for both. There's the line formula. There's a kind of a modified structural formula of the other one. Yeah, here's a good example right here. Here's a molecule with 2 methyl groups on it. Let's look at the longest chain. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7? All right, so 7. We got a 7 going right down through here. 7, so it's a heptane. And we've got 2 methyl groups and 1 ethyl group. Okay, now this methyl group over here is closest to this end. So the very first substituent you get to is methyl. So this end right over here is going to be carbon number 1, and this end over here is going to be carbon number 7. Okay? And I'm sorry it's got a black background. It's not very easy to... Oh, look at that. 2, 3, 4, 5, 6, 7. I didn't know it would do that well. So there's our 7 carbons. So the ethyl's going to come first. So it's going to be 5-ethyl. Should have let you name this one. But we got methyls on carbon what? 2 and 3. Okay, how do we do that? We put a 2, comma, 3, dash. Dimethyl. Heptane. And we're alphabetizing off of the E and the M. Dimethyl does not go before ethyl, even though D goes before E in the alphabet. That di is a prefix. It could be a prefix for anything. Ethyls, methyls, isopropyls. It could be a prefix for anything. So that prefix isn't going to get it ahead in the line for naming it. We're going to always alphabetize off the name of the substituent, not off the prefixes. Okay, so this is an example we haven't had yet. It's got 2 numbers, 2, 3, dimethyl heptane. This is all IUPAC names. There's your 6 rules. Okay, never forget rule number 1. It's at the top of the list because that's where you start. You start with finding the longest chain, not just for alkanes, for any organic molecule. Your starting point is find the longest continuous chain. And that's going to get you your parent name. And then you start filling it out from there. Okay, so that's not only rule number 1, it's numero uno in the way of rules. Most important rule. Okay, now here, let's see what's a good example here. Okay, draw that. Draw that. 3 isopropyl hexane. Now, remember from yesterday, you might remember that I said I always start with the parent name. Draw your structure of the parent name. Don't put the hydrogens. The hydrogens go in last. Yeah, why don't you draw the structural formula and the line formula? I would start with the structural, if I were you, and then draw the line. I'll show you in just a second. Okay. Well, let's make an isopropyl group. There's an isopropyl group right there. Hexane. We got hexane. 1, 2, 3, 4, 5, 6. Thanks to Blessing and Chelsea. All right? And on number 3, 1, 2, 3, let's put an isopropyl. That's that molecule right there. So let's see how we would draw it. So hexane, 6 carbons. We're going to put an isopropyl group right here. It gets a little busy, doesn't it? Got hydrogens all over the place. Is that it? What did I leave out? What? Right here? Right there. I left that out because that often gets left out. Don't leave that out. Look at every carbon. See, without that there, you can see that carbon coming down there only has 3 bonds to it, right? And it needs to have 4. So you need to get a little hydrogen right in there. On your Chapter 10 homework, I'm going to be looking for every single hydrogen. All right? When you turn that in today. I want to see every hydrogen. I want to see that you know that every carbon needs to have 4 things around it. And we're on alkanes. They're all single bonds. You just got to make sure every carbon has 4 things around it. If it has 2 carbons, then it needs 2 hydrogens. This carbon here has 3 carbons. It's got a carbon, it's got a carbon, it's got a carbon. There's one right there. All right, now line, we would go, here's 1, 2, 3, 4, 5, 6. And the isopropyl, there's the carbon, it comes down, and it's got it's got 2 carbons on it. That's the line formula. Yeah. Well, it could be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Could be like that. It could be 1, 2, 3, 4, 5, 6. I could have started here. 1, 2, 3, 4, 5, 6. So here's my 3. Those are all the same molecule. It's got an isopropyl on the 3rd carbon, 6 carbons long. Can be drawn a whole bunch of different ways. Like what?
Like if you pick like a point and use the 1, 2, 3 square one instead of
No.
Nope.
Can't do that. You can't do this. 1, 2, 3, 4, 5, 6. That's 7. 1, 2, 3, 4, 5, 6. I told you when your pen hits the ground. 1, 2, 3, 4, 5, 6. Did it again. See that? See how easy it is to? You just don't want to count. 1, 2, 3, 4, 5, 6. What you're saying is something like this.
Yeah.
Why can't you do that? That's a good question. Why can't you do that? That's a what?
That's an ethyl.
That's not an ethyl. It's got 3 carbons. 1, 2, 3. That's a propyl. It's not an isopropyl. That's got the carbon attached on the end. All right? So that is a propyl group. That's 3-propyl hexane. This is 3 isopropyl hexane. You see the difference? See the difference? That is not a propyl group. That's an isopropyl group. It's attached at the center of the 3 carbons. Okay? So, no, I'm glad you asked that question because that shows you the distinction between a propyl and an isopropyl. Yeah, it's got 3 carbons, but not attached on the right carbon, on the correct carbon. Good. All right. Well, this is how you learn this stuff, by just trying some of these things and seeing what does look right and what doesn't. Let me see if I got any other examples here. No, that was the last example. We'll skip over some of these. Let's just do a line diagram real quickly. Heptane, 1, 2, 3, 4, 5, 6, 7. 2, 4 dimethyl. So 2, 4. 3 ethyl. Boink, boink. So there's the line diagram. And I'll just do a condensed formula. Heptane, we got a CH3, CH3, that's carbon number 2. Carbon number 3, CH, CH2CH3, that's an ethyl group. And carbon number 3. What should carbon number 4 look like? Yeah, CH, then what? What do you call them? Parentheses? That's where we're at. We're on the 4th carbon right there. There's a methyl group. There's 7 carbons, so that's 4, 5, 6, and then what? What's the 7th carbon going to look like? CH3. So on the other end, there's the condensed formula. All right. Structures and names. Did everybody get that? Structure and names is unbranched. Okay. Butyl, there are 4 different substituents. I've only had you learn, I've only had you learn normal butyl and tertiary butyl. There's secondary butyl and isobutyl. There are others, so if you come across them. All right. We're going to look at this right now. What do we mean by isomers? You've already seen this word, iso. Here's butane. Do you have four carbons together? Yeah. 3. That's good. 3. Let's put one. Oh, that's exactly what I need. Okay, what are isomers? These 2 molecules here are isomers of one another, and they are. Let's look at this. Let's look at the molecular formula. So I'm going to count carbons and hydrogens over here. We got 4 carbons. How many hydrogens? 10. C4H10. That's the molecular formula. Now let's look over on the right. How many carbons are there? Count the hydrogens. How many hydrogens are there? 10. These 2 molecules have the exact same molecular formula, but different structures. Here's butane. Here's isobutane. These 2 molecules are not superimposable on one another. They have the exact same molecular formula. 4 carbons, 10 hydrogens. But I can't lay this one on top of this molecule and get everything to lay on top of one another. These are different compounds, but they have the same molecular formula. This is why in organic chemistry, starting with an O, we can't just rely on molecular formulas. They don't tell us. I mean, as you get on up to bigger molecules, pentane, hexane, octane. Octane is octane, C8. Straight chain of 8 is going to be 2n plus 2, right? 2 times that is 16. That's octane. 1, 2, 3, 4, 5, 6, 7, 8. It's octane. 1, that's 2, 3, 4, 5, 6, 7. That's going to have the same formula. 1, 2, 3, 4, 5, 6. That's going to have the same formula. These are all isomers of octane. I can go on and on and on. Octane will have, I don't know what, 8 or 10 different isomers of octane. What are they? They will all have that molecular formula, but they will have different structures. That's isomers. That's what isomers are. Are they different? Well, look at them. They are different. This thing boils at almost 0 degrees centigrade. This boils at minus 12 degrees centigrade. So you say, they're the same molecular weight, they have a little different structure, they have different properties. So melting points are different. This is isobutane and butane. Now, okay, this is what will happen in each of these chapters. You need a 3x5 card of at least that molecule right there. That's the common name. This molecule has 2 names. That is not its IUPAC name. You tell me what its IUPAC name is. What's the IUPAC name of isobutane? 2-methylpropane. So that's why you can figure out that it's called 2-methylpropane from the 6 rules I gave you, right? You can't figure out that it's called isobutane from those 6 rules. That is its nickname. It has a nickname, or we call it a common name. So you're not going to learn the common names of every common organic compound, but the ones that are really common, like acetic acid. You don't need to write this one down right now. That will come in chapter 14. Acetic acid is the acid that's in vinegar. That's its common name. It's not its IUPAC name. We'll see what its IUPAC name is when we get there. So you need a 3x5 card on that one. So you have 10 3x5 cards, methane through decane. You have 6 3x5 cards, the 6 substituents. And now you have this one molecule that has a common name and an IUPAC name. They all have IUPAC names. Why do you need to know this? Well, on a quiz or an exam, I could say, draw isobutane. You go, oh man, I can draw any molecule if you give me the IUPAC name, but I can't draw that one because I don't know the structure of isobutane. All right? So what are isomers? Isomers. Same molecular formula, different structures. Isomers. All right. Cycloalkanes. Look how much progress we're making. Cycloalkanes. So let's get back to our hexane. Here's our hexane. That's hexane. 6 carbons. Now let's wiggle this around a little bit. I told you that these single bonds you can rotate around and look. Now, not just because of the model, this is kind of what the molecule can do too. But it's long enough now that this carbon number 1 and carbon number 6, can get close to one another. And notice I can clamp that together. I'm taking off 2 hydrogens. And I've got 6 carbons. In a ring, each one of them has 2 hydrogens on it. I can't call this hexane. All right? Because hexane is a straight chain. This is cyclohexane. Cyclo. cyclized. Got 6 carbons in a ring. So cyclohexane. The structural formula would look like this. And each one of these carbons needs 2 hydrogens on it. I mean, look, every one of those carbons now is bonded to 2 other carbons. So every one of those carbons needs to be bonded. And I would put the hydrogens outside the ring like this. Somehow writing on here with it sticking up in the air is a little hard. All of a sudden I feel like I'm left-handed, or trying to write left-handed. Okay? And notice what this is. These are on the outside of the ring. So don't draw one hydrogen in the ring and one outside the ring. It gets pretty ugly inside the ring that way. And it actually is a little bit more accurate to have them pointing out like that. There's the model, there's the structural formula, and you're going to love the line formula. That's the line formula. 6-membered ring. We ignore the hydrogens. We draw the outline of the carbons. And these are all cyclohexane. Okay, there's now notice with cyclo. Let's get 3 carbons here. Now remember, I told you these are 109.5 degree angles. Now to make, look what would have to happen to make cyclopropane. Take that hydrogen off of there, take that hydrogen off of there. What do I have to do now? I have to bend this around. What that likes to be is a 109.5 degree angle right there. But if I make cyclopropane, which you can make it with some difficulty, this is not an easy molecule to make, you have to constrain those bond angles now to be 60 degree angles. That's the angle. Look at that. Look at, even in the model, the bonds are strained. All right? For this molecule, that feels like a size 6 shoe in a size, or a size 6 foot in a size 3 shoe. This molecule aches to get back to that. And I don't know how unstable this is, but some organic molecules are so unstable that you can't ship them. You know, you dropped it, it would explode, because it is so uncomfortable in the configuration it's in. Now if we went to cyclobutane, we've gone from 60 degree angles to 90 degree angles. That's cyclobutane. Still constrained, not as bad as cyclopropane, but not natural. And if we went to cyclopentane, you actually get to 109.5 degree angles. So by the time you get 5 carbons, 6 is really common. Cyclohexane is a common organic solvent in the lab, cyclohexane. So it forms pretty naturally and pretty readily. So these are cycloalkanes. I'm looking over here right now. We've got a cyclohexane, but we've got a chloro group and a methyl group, and they're giving precedence to start numbering right there. So it's 1-chloro-3-methyl cyclohexane. So the parent name of the molecule is cyclohexane. That's its parent name.
So how do you know what is stuff number?
How do you figure what out?
What is stuff number? Where to start?
Where to start numbering? Well, let's take a simpler one. Let's just take, here's cyclohexane, and let's say we have a methyl group right there. Actually, in this case,
Name tells you if it says 1 chloro, that means the carbon number 1 is going to be the one with the chloro.
yeah, but I think their question is, how would you know to number it that way? Yeah, yeah, we can tell that from the name, right? The 1-chloro is telling us that where the chlorine is the one,
The carbon.
carbon number 1.
Yeah, but how would you know that if you were creating?
Like if it was just a drawing, right?
Yeah.
Yeah. Okay, they're giving priority to the chloro group there, but let's go back to this one. We've got cyclohexane. Here's this is a little bit of a confuses students. There's a methyl, so there's methyl cyclohexane, and in this particular case, I don't need a number. We got a substituent on a carbon. That definitely is carbon number 1, right? It is distinguished from all the other carbons. Why? Because it's got a methyl group on it. If you were going to call anything carbon number 1, that would be it. So, I mean, technically it's 1-methyl cyclohexane, but the 1 is unnecessary. Now let's go one step further here. Put a methyl group there, and let's put a methyl group there.
It's the same thing, right?
It's the same thing as what?
If you start from this one, it'll be 1, 3, and then if you start from that one, it'll be 1, 3.
Right. It doesn't matter. Right. I could call this 1, 2, 3. What are you going to do? You're going to count over to the next one, the shortest distance. You don't go clockwise or counterclockwise. You go the shortest path. Okay?
So let's say it was over here, you would go this way.
Yeah, so if it was, well, yeah, let's look at that. So that is going to be 1, 3, and in this case, we would use both numbers, 1,3-dimethyl cyclohexane. And if we had, now take a look at this. What would you call that one?
It would still be 1, right?
You got to that answer really fast. How'd you do that? Yeah. Okay. No, that's good. That's good. 1, 2, 3. 1, 2, 3. Now notice, now here's where you got to use your mind. If I picked that up, I could lay it right on top of that, couldn't I? So you say that looks different from that. No, that is, if I named that, it'd be 1,3-dimethyl cyclohexane. Everybody see that? This and that would have the exact same name. Why? They are superimposable on one another. I can flip that over. So be able to do that in your mind. Be able to geometrically kind of look at things and say, is that really different? Is that something different? Now, if I came along here and I put a methyl group right there, that is different. What is that? One, 4. That's 1,4-dimethyl. One, 2, 3, 4. Dimethyl cyclohexane. I'm not going to worry too much about the chloro. Just over here, They just decided, okay, we're going to start counting from the chlorine or from the methyl, and they picked up from the chlorine. Yes.
I think it's because your slide says that you, for the cycloalkanes, you still for, because place substituents in alphabetical order. So I think that's why they did the C first. For the chloromethyl?
Yeah. So the chloro does come first. Well, it's going to come first for a different reason. Yeah. So we're not going to put the chloros and the bromos and the iodos just alphabetically in the whole thing. So, I mean, it does look like we're doing it right here. But all the halogens are going to go out to the front. And then all of the alkyl groups are going to go in the middle, and then we're going to get the parent name. So, conformations. Well, let me just, well, what do I mean by conformations? Let's look at, the best way to look at conformation differences is cyclohexane. So let's get over to cyclohexane here. Yeah, so here's cyclohexane. And cyclohexane can get into two conformations. This is the, well, here's the boat. So take the two ends and pucker them upwards, and it looks like a little life raft. Can you see that? That's where they're coming up with this boat conformation. The molecule hasn't changed its structure. It's just changed its conformation. It's gotten into a little different conformation. But, like, you know, you're sitting, you stand up. Nothing's changed by the way your body's held together. You're just in a different conformation. You're standing, not sitting. This is in a boat, not a chair. A chair is we'll drop one of them down, leave one of them up, and drop one down, and you get a chair conformation. Still have the four that are kind of flat. Here's the back of your chair, and here's where your feet are resting in kind of a lounge chair, okay? That's conformation. So if you hear that term, it's just a different shape that a molecule can get in without changing its structure. Not changing its structure at all. So that's what we mean by conformation. It probably will hardly ever come up again. It'll come up in biochemistry when proteins get into different conformations, and that's really critical because they don't change their amino acid structure, they just get into a different shape. So that's what we mean by conformation. Okay, let's take a few minutes break. Well, let me finish the properties. We'll take a break till 12:30, and then we'll do reactions when we come back from the break. Remember, I told you there's going to be four things. There's going to be, what are these? What are alkanes? How do you name them? How do you draw them? And how do they react? So, properties of alkanes. Alkanes are nonpolar molecules. The carbon-carbon bonds, the carbon-carbon bonds for sure are identical. They're nonpolar. They equally share electrons. So there's no polarity around a carbon-carbon bond, and there's very little polarity around a carbon-hydrogen bond, leading to a fairly nonpolar molecule. It's got a whole lot of nonpolar bonds. That makes it nonpolar. Water is polar, and that means that these things are not soluble in water. Like dissolves like. Water is a polar solvent. It will dissolve polar substances. But nonpolar substances like gasoline, oil, whatever, you know this. You can't dissolve olive oil in water. It's oil, and it doesn't dissolve. It floats around in there. They're less dense than water. That's why gasoline floats on top of water. They're relatively odorless. Even natural gas is odorless. We better take a break. Let's take a break, and we'll come back right here.